present, please ask the students to join the live stream.
Okay.
Okay.
Please ask the students not to ask for the permission because the meeting link has been already closed. We are starting this meeting in 2 minutes. And please here ask the student not to ask for joining. They should join the live stream. Yes, start. So we are now starting our event. First of all, I want to ask all this CR, please ask the student not to ask for the entry permission. The entry has been closed. They can all join the live stream.
Okay, done.
A very good afternoon to all of you. I would like to extend my special welcome to our guest speaker, Mr. Tanmoy Roy Choudhury and Mr. Vishwajeet Jaina. Thank you, sir, for being with us. As you all know that today we all have gathered here to celebrate a very auspicious occasion known as National Science Day. You know, the science is related to everyone's life, the deeper you want to go. Just let me brief you something about it, how it all started. In 1986, the National Councils of Science and Technology Communication proposed that 28th January should be celebrated as National Science Day in order to honor the invention of Raman effect, which was done by a famous physicist known as. So this was all that how it all started. You know that science is a very big era. If we come to close to defining it, we'll find that more we are going, the more new things we are finding. Every day we are finding new discoveries, very amazing thing happening in the world of science. We cannot cover all, but definitely we can cover some of the important and some of the interesting things about science. In order to do that, we have our guest speaker, our first guest speaker of the day, Mr. Vishwajeet Jaina. He is a chief manager in R&D department hall, Hindustan Aeronautics Limited. He is an MTech in Solid Mechanics and Design from IIT Kanpur. He has around 26 years of experience in equipment system design and development of industrial application. So, I will please ask you to join the mic.
Thanks, madam. Good, good evening and Jai Hind. So, should we start? Okay.
Jai Hind, sir.
Jai Hind.
I would like students, if they can switch on their camera, it will be more interactive session.
In fact, being in English, and that's why I will be using Hindi a bit, which is our mother, our Indian language, our national language rather. And to go ahead with the bridging between physics and mathematics through vibration, I would like, and how they're related, we'll be discussing. Before going to deep to me, and I hope you know there are two types of questions. One is intended to know what is beyond, and the other one is to test what is being spoken. I hope the questions will be first type, and if at all, I won't be answering those questions on this platform right now. I will take quick possible. Now coming to mathematics, our agenda today, this evening will be some concepts of mathematics will be discussing, then vibration, characterization of characteristic equation, dynamic stability, dynamic balancing, and some applications that we have gone for in HL. Now, this is only one slide which gives a few concepts, but we'll put more time on this. We are trying to find things that is available with us. We start with one tree, one ball, one man, one cow. From that one, we start 1, 2, 3, 4. Say, although they say 24 hours a day, but for them 6 months is 1 day. Because for them, sun rises for 6 months. Or else you look at those people who move to the outer space. For them, there is no night. They are always before the sun. For them, the time is not changing. So time develops, time concept develops only when there is a change around us. Without those changes, time is also not there. But if you look into it, you find a three-dimensional feeling. So are the three-dimensional things we are looking around are really three-dimensional? These are perceived, these are all relative terms. That is the logic behind it. We develop so much of mathematics. Now, after going through these dimensions, let's go to concept of orthogonality. Orthogonality, generally we understand something that is at 90 degrees. Then they are orthogonal. For example, suppose you are looking from top of a spiral, feel the height railway track or close to it is unable to sense the speed of the train because he is directly in front of the train, so the speed of the train is not visible to him. So speed of the train for that person is orthogonal. Similarly, in the spiral case, when you are looking from the top, You are finding the person moving in a circle, but the person who is now coming to domain. To go to domain, I will show you one picture. My first picture. This is the top view of LCA aircraft. Now you see what is happening. This is a 3D object, but you have taken the picture on a 2D, so you are unable to look at what is there on the bottom of the aircraft. So a three-dimensional thing, a three-dimensional object is having a domain of 3 dimensions, X, Y, and Z. But when you are taking a picture from top, you are transforming the three-dimensional object into 2 dimensions. The other dimension that is not visible to you on this photograph are in null space. So the three-dimensional object, the aircraft is in domain, the photograph is its codomain, and those things that is not visible to us, those doesn't create any image on the codomain, so they are in null space. Every day when we look at our mirror, our front face we see in the mirror, but what is there on our back of the head, it is not visible. So the points on back of my head are in null space. My total head is 3-dimensional. Its image in the mirror is 2-dimensional. So there is a transformation, but certain points of my head are not creating any image on the mirror. So those go to null space. After that, let's go to negative numbers. The point is, mathematically, when we say negative things, negative values, what do we mean? In physics, those are vectors. Let's say height and depth. Let's consider height and depth. Both are distances. When I say height of this pole is 3 meters, that means I am taking reference of height as a positive element. When at the same time I want to say about the depth of a well, then I will represent it in a negative number, with a negative number, but the distance is absolute value. Suppose 5 meter minus 5 meter is the depth. Depth is 5 meter. That means minus 5 meter. So the absolute value, the distance is 5. If for pole, if it is 3 meter, the absolute distance is 3 meter. The absolute value is the distance, but to represent height or depth, we take negative number and positive number. If I take depth as a positive number, then it is negative. So it gives a sense of direction. That's why it's a vector. Similarly, if at all you look at area, generally area is called scalar. But suppose you have got a transparent balloon and you want to paint it inside. The inner surface you want to paint. So how will say that? You will ask the person to paint the inner surface of the balloon. Although both the inner and outer surface are of same value because the thickness is very less, still we are putting a directional property to the area. Like if I say hair grows on head, hair always grows out of the head, not into the head. So hairs are having a directional property. The area of our head is having a directional property so far as hair is concerned. Here, there is something very special to it. We say negative multiplied by negative is positive. How it is so? Now we all know multiplication is repetitive addition. So if I give the 2-meter clock to somebody and the similar clock to another 5 persons, 2 into 5, it becomes 10 meters. So you have got positive value 2 and 5% are also 2, 5% are also positive. So 5 into 2 becomes 10. Why these are positive? Because these are naturally available to us. But as we discussed right now, negative number physically indicates a directional property. Suppose I ask somebody to make a hole having a volume of 5 cc, 5 cubic centimeters. Now that person, suppose I am taking hole is a negative and gathering a mass is positive. So minus 5 cc material. Suppose I asked him to make 3 holes, so minus 5 into 3, so minus 15 cc. 5 cc material he was removing, but I am asking him how much he collected. So removal and collection, their directional property is opposite to each other. So minus 5 for collection again minus 3. So minus is plus 15 cc material he has collected. He had made a hole minus 15 cc, but collected a material of 15 cc. So minus into minus becomes positive. Now, coming to imaginary numbers. This is the best part of it. Generally, imaginary numbers are used for interpretation of physical events that is happening around us. See, just now we discussed now, that was making of a hole and collecting material. They are a shift of paradigm. The way you are viewing at the thing. Similarly, imaginary number is also looking at how you interpret some value when it is multiplied by itself, when it is repeatedly added to itself, it creates negative number. Generally, in India, there is a problem of nationalism. If you look at this, so negative things, when we say negative, negatively directed things, it has a different meaning altogether. So, see, for example, to a child, if you say, don't do that, no image will be created in its brain. If you say, well, do this thing, go to, instead of saying, don't play, you say him, but when no image is created. Similarly, with that, to really happening things. It has got no impact on the reality, the real line, physically what you can imagine, but it is having an impact on the event. We'll go to that, how we are doing it. Now, coming to time and frequency domain, we'll go to it. With that background, let's look at vibration and putting it into the physics. Responsible for creating this Z displacement. So basic equation for this thing will be m z double dot means this is acceleration along z direction. Now the double derivative of z with respect to time. This is c. This is the damping constant, which is proportional to velocity at which it is moving. See, this force is proportional to acceleration, keeping the mass constant. This c is proportional to velocity of this mass, and k is proportional. K multiplied by z creates force. So all the three, when they are added together, they are equal to this force. So this is in that time domain. We are looking at acceleration, velocity, and displacement. When we transform it into frequency domain, the equation will be something like this. This is Laplace transformation. So ultimately, we are not concerned about this. We are concerned if at all I put f amount of force, how much displacement will be there? And if at all I change force f, what will be this displacement? And moreover, most important thing is if this f I change very frequently, quickly, will this z be proportional to f? What will be the behavior of this z? For that, we divide z with f. This is the response, this is the force. So their division will depend upon this equation. See here, Zs is taken common, so this part comes out. And when Zs is divided with Fs, the left-hand side goes down and this becomes the equation. Further, if you look at more closely, you'll find this equation will get transformed into this, where the equation depends on some coefficient c by m, some coefficient k by m, s and m. Here also we put k by, suppose we put k by m is omega m, undamped natural frequency. C is damping, so critical damping coefficient is this, and C by Cc is zeta. Then we'll find this equation. Ultimately, this is the equation which says with change in frequency, this value will change, and this also depends upon zeta and m. Further, we can reduce this equation to this value. So this is presentation I will share with you. You look at it more closely later on. As I told, there is an absolute value relative from relative value. We can get absolute value. Suppose you put this way. Suppose I understand the equation we had reached over here, and the same equation I have put over here also. Now, if at all I replace it, this s with j omega, then the equation will be turned to this. And here, if it is going to 1000 hertz, at 50 hertz, this omega becomes 50 hertz. We know omega n was 50 hertz. When it is running at 50 hertz, then this case will happen. This thing will happen. What will happen? The torque that is developed by this motor at a particular displacement, rotational displacement, angular displacement, there will be a relation that will depend on this k and zeta value. Higher the zeta, less will be the displacement, and the higher the stiffness, torsional stiffness, higher will be the displacement. Are you getting me? Madam, I need a little, yeah, because it becomes so monotonous.
Yes, sir. Mathematical part may be little bit difficult for the students, but I don't know how far they are receiving. Students, you can converse with the sir.
Okay, right. Okay, let me put into figures. It will be much better. You see, when the started to increase its speed of loading, this will be the amplitude. With various zeta, omega m at this point, at this axis. And before that, and after that also, you'll be facing less vibration. But at the natural frequency, you'll be having maximum vibration. And when you are increasing zeta, this vibration level will reduce. That is what this representation says. But what is happening to this angle? It is lagging by 90 degrees. And when omega is too high, it is lagging by 180 degrees. That means that is represented over here. The phase difference will be there. What happens in this case? Suppose you are forcing the spring to, you are hammering the spring with the different frequencies. When your heating frequency is equal to natural frequency of the system, then at the moment you are trying to heat, the mass will be moving backward. You won't be able to heat it right at that point. But it won't be at its peak. The displacement won't be at its peak when your force is trying to be at peak. That is what it will happen over there. The same thing we are putting over here also. When we say stable system, the drop of response will be at minimum minus 6 dB per octave. This is how it drops. I think it is getting more mathematical. Why I am putting these things before you? Because whatever you learn in your science, this thing is taught to you. But the nature, the physics never behaves this way. The behavior of physics, the behavior of physical events is something like this. Here you have got all those three elements: mass into acceleration, damping into velocity, spring stiffness into displacement. Along with that, there is cubic nonlinearity because of softening of the spring or hardening of the spring. Whatever we are taught in our in our colleges, we are taught with linear spring. What is happening with the linear spring? But practically, we generally get this type of situation, and the behavior becomes something like this. In linear systems, you get maximum amplitude at omega equals to omega n. At natural frequency, you will get maximum amplitude. Whereas in practical, in real world, you get dumping action, dumping equation. This is dumping equation where as you increase the frequency from 0, the amplitude of vibration increases, but it never maximizes at omega equals to omega 1, but it goes up at some other frequency, it maximizes. Then from here, it doesn't follow this path. It falls directly from here, this point. So what happens? You will be feeling the vibration is increasing. At certain point, it all of a sudden drops. When you are increasing the speed. And when you are reducing the speed in the opposite direction, the vibration of course increases, but it doesn't go to that level which was apparently available when you are increasing. You are increasing and finding a amplitude of this value. Whereas while coming back, you won't be getting this value of amplitude. You will be getting something here, and that will again drop. So in forward movement, you will be having different amplitude, and when you are returning, you will be having another amplitude. So that will be a hardening spring. Like here, in such cases, you will be having hardening effect. Like suppose this disc you are trying to rotate. So this vibration will increase, then all of a sudden drop. Then when we are reducing the speed, it will go on increasing, then it will fall. But while proceeding, the amplitude will be more. While reducing, the amplitude will be less. The other way it will happen when you are using such type of systems. This string may elongate, creating a softening effect. Here, what hardening effect? Here, softening effect. For softening effect, what happens? When you are increasing your frequency, you are driving up, the amplitude is less, and when you are returning, the amplitude will be high, and all of a sudden it will drop. So the point is, mathematics says this one, and this one, all the three can happen. And we have to interpret where it is happening physically. Now, same ducking equation we are putting into different mode. Suppose you are going to a temple. There, you get bells. You hit a bell. What happens? A very small ringing you will find, and it will gradually diminish. What is happening at that particular point? When you are hitting it, you are creating an impulse on the body. That is a step function. All of a sudden, at time t0, the force is maximized. So, all the harmonics, all the natural frequency, and its multipliers, all will be activated altogether. So, the vibration, the energy will be dissipated at natural frequency along with its harmonics. In this case, in ducking equation, what happens? The vibration, I'll go a little forward and I'll show you. Okay. In ducking case, before at 1/3 of natural frequency, the vibration will increase. Then at natural frequency, it will increase. Then 3 times of natural frequency also, it will show higher displacement. Here in this case, what is happening? We are keeping a force of 0.2 with a stiffness 0 and some this mm, Jasper, that damping 0.08 at omega when omega equals to 1, that ratio of natural frequency to the frequency at which the system is being run. At that point, you will find several frequencies, several waves are moving through the system. You see, you have got this wave also, this wave also, this wave, all the waves are acting over there. So if I tell, this is with respect to time, the displacement with respect to time. But if you look at the velocity with respect to displacement, it will create some very, you can say, abstract type of movement. So you cannot realize actually what is happening, you will get confused. Similarly, you see, only here we have got A.2, whereas here we have increased the force to 10 and we have reduced the damping. Then what is happening? There you have got some very smooth curves. Some are quite regular, but here it is very chaotic. And if at all you take your velocity to displacement this graph, it is also quite confusing. Now, the point is, in real world, they both work together and they create this type of movement. Here, there is a periodicity, very regular pattern, but here you won't get any regular pattern. So these are all happening in vibration. And why it is happening? Because all the waves that is effective at each point of time, they superimpose and create this type of motion. And to segregate that, we find difficulty and we say practical and theory are two different things. But if at all somebody can formulate mathematically these situations clearly, then he will get the results as per, it will completely mimic the events. Yes, that is what we have shown you. This is one wave, this is another wave. All these waves are effective at particular moment. At each moment, suppose you take 2, you will get a value for this wave, another value for this wave, another value for this red line, and another value for this blue line. All will be superimposed and they will create such movements, such vibrations. So if at all you look at this area, what is it? This is a beating. This is another beat. They are regular ones, but they are regular with respect to each other. But if at all you take 0 to 2, they are increasing, then decreasing, something like that. And if this frequency is very high, then what will happen? You will get this type of beating phenomenon. So how to go about it? Now at natural frequency, what will happen? Your displacement will be increasing till it fails. So we need to stop resonance, that is running of the system at natural frequency. So these are various plots we have developed. If at all you get a higher damping coefficient, you see, as you increase the damping coefficient, the periodicity of the response is decreasing. You see, here at 2 you have got some wave, but here it is reduced. Here it is much reduced. What is the difference? You have got damping higher here than the previous one, and here you are having the maximum damping between the 3. In this case, what is happening? You see, omega n is 7, natural frequency is 7, and the response we are getting this response when the system is run at 3 radians per second. This is 7 radians per second. In that case, you will be getting some response like this. But keeping same omega n, if you increase the speed, this frequency, then you will find a behavior like this. This is also regular. If you say, you can say regularly irregular. These are regularly irregular. Now go to a little more. What is happening? When you are increasing the speed, you are getting similar vibration, but you see the amplitude is much reduced. Here the amplitude is 0 to, it is 0 1 over here, whereas here it is much more than 0 2. So near the natural frequency, this amplitude increases, and beyond natural frequency the amplitude decreases. We have put forth a case to explain the modes of vibration. Suppose this is a plate. This plate is this is held at one side, and a force is put over here, a variable force. Then it will have different modes of vibration. This is first mode vibration. That means that this is the first natural frequency, how it will behave. At second natural frequency, how it will behave. These are you say the shape, the movement, the deflection of the plate is different at various frequencies. As the here we have put frequency, and here the deflection parameter. You see, this is the first mode. At very low frequency it is happening. This is the natural frequency of this thing, and you will get higher amplitude. Here, this is the second mode. This type of vibration will happen at a higher, you can say integral multiple of first natural frequency, and the amplitude will be reduced, and so on. As you increase the mode, the amplitude of vibration will reduce. Now, this axis is in frequency, and this is in deflection. Deflection can also be put into dB, 20 log static dynamic displacement divided by static displacement. Log base E is the dB value. Now, that is a parameter which indicates how much margin, how much gain you are getting for a particular input. Now, here you see, here we have got frequency on this line, and this is the response line. This is in dB, and this is a real axis. We'll come to it later on. Now you see, this one is represented over here. This second one is represented somewhere here. And as you increase the frequency, this will be dropping, and then it will drop to a particular here frequency. It will drop completely, and this droppage for a stable system must be minimum -6 dB per octave. This has to be like that, else the system won't be stable. It will destroy itself. How it is done? We are coming to that again. If you look at this equation, this is a quadratic equation, and we can very well resolve it into factors s plus a whole multiplied by s plus b, and both will give the roots, and that will define whether the system is stable or unstable. The roots of S can be real or imaginary. When it is imaginary, it will have a real part and an imaginary part. When the real part is negative, that indicates the system will damp itself. It won't go on vibrating. When the real part is positive, be sure the system will never stop vibrating. That is what represented over here. This is the imaginary axis, this is the real axis to plot the values of S, the roots of S. If the roots of S falls plus the negative side, this is zero line for real axis, this is 0 point origin. To the left of origin, if the roots of S falls, that means the system will be stable. How much stable? That we have to find out. Now, like suppose the root falls here on this real axis, then the response will be dropping. Initially, it will be high, then it will drop with time. If this point moves further left, that means the damping will be very quick. The displacement, the vibration will reduce very quick. Hello. Well, now if at all the roots of this falls on this axis with zero real value, then this will go on vibrating. And if it is on this side, then as we discussed earlier, this vibration will go on increasing. An example we have put over here, the roots of S will be getting at these 2 points. They are conjugates. You see, S equals to -2 minus 5j, and here S equals to -2 plus 5j. So -2 plus minus 5j. So they will be on this side. So the system will be stable, no doubt about it. But can we increase the stability? Yes. When we can move these 2 points towards this side, then the system will be more stable. And if mathematically we plot it, we'll get something like this in 3 dimensions, where the real axis is on this line and the imaginary axis